Artificial intelligence, AI. It's in your phone, your home, it's even in this video. And now, AI is being tested in weather prediction models, paving the way for even more accurate forecasts in the future. Depending on who you ask, AI is either going to save the world or destroy it. But what does it mean for something as everyday and as essential as predicting the weather? We're recording this in 2025. Of course, with how fast AI is moving, this video is likely to become dated very quickly. But that's exactly why we're making this video now, because the questions we're asking today are so important for the future. How does AI weather prediction work? Could it replace the traditional physics-based models we've trusted for decades? Will we still need human meteorologists? Or can AI be used responsibly alongside traditional models and human meteorologists to create a better future for us all? Before we get into all of that, what even is AI? Many of us use it every day, but do we understand how it works? Or what it could become? Have you ever used AI for anything?
Not specifically really, but I just noticed it come up on my phone when you do a search for something.
I'd only use it to summarise my CVs. And
I use it for my assignments and that.
Yeah, well, how do you use it for your assignments?
Just put the questions in and it comes out.
Yeah?
But I hope my teacher's not watching this, so yeah.
Do you think you might be using it, but you'll be unaware of?
Actually, I find that really scary because it's like you feel like you're being watched.
Are you worried about how artificial intelligence might change our lives in the future, or is it something that you'd be excited about?
I think I'd be excited about it, but of course it needs human control now.
Yeah.
Obviously.
I think most of the jobs will be taken for sure. If not, I think future life is going to be much more easier than how it was back then.
It's a tricky one, isn't it? Because when you're talking about detection of early stages of cancer and medicine and the good that it can do, then of course we want it. We definitely want it. It's going to have its pros and it's going to have its cons.
Mostly when it comes in the wrong hands. Yeah, that worries me a bit.
We don't want a situation like, have you ever seen 2001
Yeah.
by Arthur C. Clarke?
Yeah. It might feel like AI has come out of nowhere in recent years, but the idea's been around since the 1950s, when Alan Turing asked the question, can machines think? He imagined machines could learn from experience, an idea that would later inspire researchers to teach machines like children. In 1956, a group of scientists at Dartmouth College were so confident in AI's potential, they thought they'd solve it over the summer. They clearly didn't. But they did kick off decades of research, hype, and heartbreak. AI went through boom and bust cycles. Big promises, followed by funding freezes, and what researchers call AI winters. Then came the 2010s. With the help of big data, powerful computer processors, and deep learning, AI finally started delivering fast. Suddenly, AI could write essays, recognize faces, even chat like a human. But what is AI, really? At its core, AI is about pattern recognition. It learns from data, millions of examples, and makes predictions based on what it's seen before. But making predictions based on vast amounts of data and continuously learning from experience isn't new. Weather forecasting models have been doing it for decades. In 1922, Lewis Fry Richardson imagined a forecast factory, a theatre of people solving equations by hand to simulate the atmosphere. He estimated it would take 64,000 human calculators, or one powerful machine. That vision became reality in 1950 when American meteorologists Charney, Fjortoft, and von Neumann produced the world's first electronic weather forecast. This marked the birth of numerical weather prediction, dividing the atmosphere into a 3D grid and solving physics equations at each point to simulate how the weather evolves. By 1965, the Met Office launched the world's first operational weather computer. As computing power grew, so did the resolution and complexity of these models. Today's supercomputers run dozens of simulations every few hours. This is called ensemble modelling and helps account for chaos theory, the idea that small changes at the start can lead to big differences later. Today's 5-day forecast is as reliable as a 1-day forecast was in the 1980s. This means earlier warnings, more time to prepare, and more lives saved. But here's the thing. Even traditional physics-based models have quietly used AI-like techniques for decades. They've used statistical methods to fill in gaps in data, approximate small-scale processes like cloud formation, and correct model biases after the forecast is made. These are all early forms of machine learning. So, while AI weather models are making headlines today, the truth is AI has been part of the forecasting process for a long time. Today, artificial intelligence is playing a bigger role in weather prediction for meteorologists such as Steve Ramsdale. Steve, when did you start using AI weather models, and which models have you used?
So I first started looking at weather models in sort of the end of 2022, early 2023. That's when there started to be this emergence of more and more papers coming out showing the value and the performance of these new AI or data-driven weather models. So there's things like the Pangu weather model by Huawei and the Google GraphCast model that have become available and that are being developed and show sort of state-of-the-art performance when compared with our traditional physics-based approaches. And ever since then, there's new models coming out all the time with slightly different approaches. And in fact, at the beginning of 2025, that's when the European Centre for Medium-Range Weather Forecasting had the first operational AI or data-driven weather forecast coming out with their AIFS single model. And so that's available to our member states and also on their website. And we are starting to now use that to help us understand how these models perform, especially when compared with our traditional physics-based approaches.
And do AI weather models work in the same way as, say, a large language model, where these models are trained on past data and sort of learn by this training?
Absolutely. The most important thing in machine learning is this, what's called truth data. So that's what we have to train the model. So we're lucky in the weather world that we have these what we call reanalysis data sets, which are the sort of best assessment of what the weather conditions are at any point over the last 50, 100 years. And what we do is we use that data on a certain resolution, because you can imagine there's huge computational costs in creating these. So we use that as the truth, and the model is then trained to look at this data and try and then say, using all of these inputs, how can I predict what's going to happen next? Then it verifies itself against that next prediction to try and update all of its parameters, all of its knowledge within its model to try and improve that prediction. And it's only after that cycle has been gone through many, many times that you end up with this final trained weather model that has looked at all of that data to be able to say, this is what's going to happen next.
Imagine two friends solving a puzzle. Jim uses maths and logic, like physics-based weather models. He's quick at calculating equations, but he needs to do a lot of sums to get the answer. Jane relies on pattern recognition and past experience, just like AI weather models, which learn from vast amounts of historical data. She's quicker at reaching the final answer, but it's difficult to see how she got there because she doesn't show her workings. Whilst physics-based models perform thousands of trillions of calculations each second to work out how the atmosphere will evolve through time, AI models are trained on past weather data. They're great at spotting patterns. But can they really understand the future of the atmosphere just by looking at its history? And which model works better, logic or intuition?
What I've found is that they're very, very good at the large-scale understanding and what we call in meteorology the synoptic situation. So that larger scale look at what does the weather actually look like on this larger scale. From my point of view, when it comes down to looking at the sort of the nitty-gritty, those bits of where we actually live, what is the exact wind strength going to be, what's the exact temperature going to be, there is where I find they are not as high performing as our traditional physics-based models. They don't have quite the level of detail I think I need as an operational meteorologist to make those downstream decisions, but they have value in showing me the overall picture, so I know where to look next.
So is that because of the resolution that they're not getting those finer details?
I think it's partly the resolution, so they're being trained on this larger scale data set, but that data set, even though it's at lower resolution, because it's being giving so many different observations, it actually can represent things quite well. What I think is part of the problem is that as it goes forward and as it's trying to produce this output, it's in how the model works. It's trying to, the way that these models work is they try and minimize something called a loss function. And that's the key thing in all of these models, is making that as small as possible. That's actually what they're trying to do.
Back to Jane, our pattern spotting puzzle solver. Imagine that every time she tries to figure out the answer to a puzzle, she's given a score. That score is called the loss function. The lower the score, the better her guess. To avoid big penalties, Jane might play it safe, making cautious guesses that miss the puzzles that have more surprising answers. In AI weather models, the loss function measures how far off the prediction is from reality. The model learns by trying to minimize that score over time. And that might explain why they're not capturing so many of the extremes that could occur in the forecast.
Part of it is to do with this sort of smoothing out that we can talk about. Part of it also is just that, particularly as climate is changing, we're seeing events that we haven't really seen before. There's been some very interesting papers in recent years looking at these data-driven weather models to see how they've performed with unprecedented events. So there's been papers on the Dubai rainfall that we had, where there was huge amounts of rainfall. And actually in that situation, the AI and data-driven weather models did very well. And the idea was that that's because they've learnt from elsewhere in the globe where this does happen, that they can then translate that to somewhere where it doesn't happen very often. But there was another study where they trained on tropical storms, but they took all the high-intensity ones out of the training data set, so it had not seen that before.
Of course, one of the things that we do with physics-based models is we run them lots of times. It takes a lot of computing power. Are we doing a similar thing with AI models? Are we able to run many, many more than traditional models?
So there are different options here as well. You're absolutely right. We can just run that same AI weather model with slightly different initial conditions to give us an ensemble. And as I said before, because they run so fast, you can create this very large member ensemble to hopefully create the entire uncertainty pattern that you'd have over the globe, to be able to know how things are going to evolve, where the uncertainties are. The other approach is a different one, where they've actually tried to learn the uncertainty. So you'd have a couple of ensemble members, and then you have a different model that looks at those and says, from these few members, I can understand the distribution that this gives me. And so you don't actually run a lot of ensemble members from different initial conditions. You run a few, and then you use this other model to kind of fill in the gaps around it.
Meteorologists know that predicting tomorrow's temperature isn't always about picking a single number. Instead, it's often more accurate to say it's most likely to be 20 Celsius. But there's a small chance it will be 18 Celsius or 22 Celsius, and a very small chance it will be 15 Celsius or 25 Celsius. This spread of possibilities forms a distribution, a kind of curve showing which outcomes are more or less likely. That curve is the shape of uncertainty, and it changes depending on the weather situation. AI models don't just run lots of forecasts with different starting points like traditional models. Instead, they learn what that curve looks like from past data and then generate new forecasts that fit within that shape, like drawing new samples from a known pattern. And there's another key difference, isn't there, between AI weather models and traditional physics-based models in terms of how they see the globe.
Yes, that's right. So the way that AI weather models mostly work now is something called a graph neural network. And this is quite a complicated idea, because a graph is not how I tend to think of a graph with a nice X and Y axis. That's not what they are. They're more of kind of a representation of a network. So each point on the globe you can consider as what's called a node, and then it's connected to those around it by what's called edges. And that allows information to pass from these various points to each other. And at each of these nodes, as they're called, there is a neural network which mimics the way that your brain works, with inputs going in, then firing down to another neuron to make a decision. Each of these has those networks in there. And what it does is it solves what it thinks are the correct equation to solve to get to the next step, and then passes that information onwards further.
The world isn't made of neat boxes. It's messy, interconnected, full of feedback loops. Traditional weather models divide the atmosphere into a 3D grid, thousands of cubes stacked across the planet. Inside each cube, physics equations simulate how air moves, clouds form, and temperatures change. But AI models, especially neural networks, see the world differently. Instead of boxes, some use graphs, networks of points connected by relationships. This is a graph neural network. Graph theory began in 18th century Prussia when mathematician Leonhard Euler asked, "Can you walk through Königsberg, crossing each of its 7 bridges only once?" Spoiler alert, you can't. But in solving this puzzle, Euler invented graph theory, a way of representing connections using nodes or dots and edges or lines. Today, graphs power everything from social media to streaming platforms. It allows Facebook to map friendships, Netflix to recommend shows, and now weather prediction is getting the graph treatment. Graph neural networks don't just look at what's happening in one place, they learn how different places influence each other. One model sees the world as a box of equations, the other sees it as a web of relationships. Both are powerful, but in very different ways. How are operational meteorologists now starting to incorporate AI weather models into their workflow?
So at the moment, we're still very much in the case that we want to understand these models. We want to know where they work, where they're going to provide us benefits, rather than just, here is another model to use. We already have huge volumes of data, such as our deterministic models in both high resolution and coarse resolution space, all of our ensembles. A new model coming in has to prove itself to us effectively. It's not the case of just, here's another model, just incorporate it. We want to understand where it performs well, where it performs badly. That's part of my role, is to look at these in a more sort of objective sense, try and understand where they're doing well, where they're doing badly, and where they can add value to us. And as you know, the trusted weather and climate provider of the UK, and hopefully for many in the globe, we're not going to rush into, this is a new thing, we have to use it now. We want to know how to use it best so that it adds value to what we're doing. Whenever there's a human involved in our decision-making process, that human-to-human interaction at both ends is vitally important. Even with language, I'm here using my hands as I'm speaking. That is part and parcel of it, and that is not coming from a data-driven model at the moment. We already have these types of models. They may not be data-driven, they may be physics-based, but they're still pushing out information, and we still need people to interpret that and understand what the impacts on society may be. It will change how we do our jobs and change what outputs we're sending, but I still think we need a human there with our hand on the rudder effectively to know how reliable these things are and how to communicate that best to the overall community.
And that human touch becomes even more important as we start blending traditional models with AI, especially in complex environments like cities. A recent study from the Met Office's Urban Scale Modelling Group, led by Dr. Lewis Blunn, showed how machine learning, combined with high-resolution land cover maps and citizen science data from the Weather Observation website, can significantly improve hyperlocal heatwave forecasts in cities like London. By enhancing resolution from 1.5 kilometres to just 100 metres, the team captured the complex temperature patterns of the urban heat island effect. This approach allows us to fill gaps in the data where physics alone struggles, especially in dense urban environments. But the potential impact of AI is expected to reach much further in the coming years. To find out how the Met Office is preparing for the next era of weather prediction, I spoke to Chief AI Officer Kirsty Dale.
In the run-up to Christmas 2022, so a couple of years ago, we saw an absolute flurry of research being published about how predominantly the big tech companies were using AI, and in particular machine learning, to produce weather predictions. So, for example, we saw Huawei published the Pangu weather model, and we saw Google DeepMind publish the results of the GraphCast model, and this really caught our attention. We really thought, this is an area that we've been looking at already, but this is something that really could help push forward the boundaries of weather prediction. So I came back in January 2023, and we set up a program called the AI for Numerical Weather Prediction. And within that program, we're developing the FastNet model in partnership with the Alan Turing Institute, which is the UK's National Centre for AI and Data Science. And together, we're developing the model and exploring how this could be used to support weather forecasting in the future. And yes, you're right, we have some very exciting results. The FastNet model is now competitive with the physics-based model, and I'm hopeful that in the next couple of months we'll have some really exciting results that we can publish.
As well as the excitement around AI, there are quite a lot of challenges that people are grappling with. What are the kinds of challenges that you've encountered?
It's important to say that AI is moving so fast that these challenges are not insurmountable, and they will be tackled in time. But some of the AI models, they currently don't present all of the parameters we need. So, for example, some of the early machine learning models didn't contain precipitation. Obviously, that's not going to work for the UK, where we're having precipitation is really rather important. They weren't also at the scale that we need, so we need really high resolution forecasts in the UK. There was also, because of the way the models work, there was an element of blurring, so it was harder to pick up fronts. Again, those are really important in the UK.
Another challenge is how the public perceives accuracy. Existing physics-based models have earned trust over decades, while AI methods are still building their reputation. What if AI helped us make weather forecasts? Would you trust a weather forecast that was based on AI?
I would trust in weather forecast made from AI. I think it is more accurate than any an average human being.
It's getting the information from somewhere, so I don't think it's necessarily that I wouldn't trust it. I think I would trust it.
No, I think the weather forecast from in Holland it's KNMI. I use it and I trust it. And when it's AI, I don't know whether I should trust it or not.
Probably not as much as I normally look at the BBC, what I normally look at. And on the Met Offices, I know it's quite good as well. But it's near Exeter, which I applaud.
Would I trust the weather by AI? Not sure I would. I think there's no replacement for the weatherman, really, or weather person.
Hello, valued weather consumer. Today's atmospheric parameters indicate a 72.4% probability of precipitation in your localized grid cell. Please optimize your outdoor apparel accordingly. Have a statistically significant day. And this is exactly why here at the Met Office, we're still going to be using human weather presenters for a long time to come. The Met Office strategy, I believe, is very exciting because it takes the positives of AI weather prediction, but it also addresses some of the challenges that you previously mentioned.
I think it's worth saying that the Met Office forecasts are already very good. We are consistently within the top 2 weather forecasting centres in the whole world. However, we are not resting our laurels. We are not sitting back. We are embracing new technologies such as AI to push forward the boundaries, to push forward the frontiers of what can be done in weather science. Okay, so I imagine a future where we really try and harness the strengths of the 2 approaches. So that's physics-based approaches, so numerical weather prediction, but also the newer machine learning data-driven approaches for weather prediction. Some of the advantages we're going to want to harness from the physics-based approaches that the physics-based approaches offer critical process understanding. So they respect the laws of physics. They conserve momentum, mass, and energy. And these are forecasts that are physically robust because you really understand what's going on in the forecast, and that builds trust. And that's going to be really important to preserve. So, for example, back in 1991, when Mount Pinatubo went up and released aerosols into the atmosphere, we needed an understanding of the physics to understand why and how the climate was going to cool. So that really illustrated why physics is needed, because there are some of these limitations of the machine learning approaches. Then we also need to start harnessing the advantages of the AI models. Now, one of the big advantages of the AI models is that they're fast, not just a little bit faster. They are some of them are tens of thousands of times faster than a numerical weather prediction model. And this is important for a number of reasons, but two obvious ones are because it runs very fast as a low computational requirement. You can run it much later to when you actually need it. And because it's closer to the time that you're actually using it, you can incorporate more observations, which means that the forecast is better because it has a better grounding in truth. So you see an improvement in the forecast. Secondly, because it's got the machine learning approaches have a low computational requirement, there's an opportunity for you to run it locally. So you wouldn't necessarily need a high-performance computer, a supercomputer, to run a forecast. Although the forecasts have been trained using a high-performance computer, when you actually run them, in the future, we've already seen some of these models that you can run on a laptop, but in the future, you could perhaps run one of these models on your smartphone.
Where do you think we'll be in 5 years' time?
I often think about Amara's law. Amara's law says that for a new technology, you tend to overestimate the impact in the short term and underestimate in the long term. And I think that's particularly true for artificial intelligence. The other thing I dwell on sometimes is that I often say data science years are a bit like dog years. So 1 year is actually 7 years. So if you think about 5 years into the future, in data science years, that's 35 years. And you'd be a very brave person who forecasts 35 years ahead for a technology. But that said, I do think that the future will see us drawing together the benefits of numerical weather prediction, so physics-based forecasting, because we need that deep understanding of the weather and the physics involved. And we'll draw that together with the advantages of artificial intelligence, including the speed, which is valuable for so many reasons. And together, I think that these two approaches complement one another, and we will see increasingly localized, personalized forecasts that really go to the heart of what people need to know in order to make decisions about their daily lives. And those decisions could be, shall I put the washing on the line? Or it could be, do I open a runway at Heathrow? Do I grit the roads? So all of those decisions, I think, will be informed by these technologies running in partnership into the future. This truly is using AI for public good.
So, where does this leave us? AI won't replace meteorologists or overnight rewrite the rules of forecasting, but it is helping us to predict the future state of the atmosphere in brand new ways and at a fraction of the time, cost and energy compared with physics-based models, meaning we can go even further and move beyond what will the weather be to what will the weather mean to me. The Met Office is working on a blended approach that draws on the strengths of both methods to deliver the forecasts you need when and where you need them. By combining the power of physics, the speed and self-learning capability of AI, and the experience of human meteorologists, we're entering a new era of weather prediction. One where forecasts are not just more accurate, but more useful, helping us prepare, adapt, stay safe, and thrive in a world where the weather is more important than ever.